In this videotape, we're going to learn how to find the area of a region bounded by two curves. Let's start looking at the general situation. We could have a curve y equals f of x, another curve y equals g of x. And we might be interested in the area of the region bounded by these two curves and the two vertical lines, shall we say, x equals a and x equals b. This region in here. Now, in class or in the book, you learned, first of all, we had to define what we meant by the region that had these curved boundaries, or what we meant by the area of such a region. And basically, we defined the area of this region to be the limit of the sum of the areas of rectangles that we fit into this region as the number of rectangles grew very large. And we assumed that the functions f and g were continuous on the closed interval a, b, and that, furthermore, f of x was greater than or equal to g of x for all x in the closed interval AB. Okay, by this I mean that if f of x is greater than or equal to g of x, the y value of this curve is always greater than or equal to the y value of this curve, at least between a and b. Okay, it may be over here that this g curve rises above the f curve, or over here the f curve falls below the g curve, but between a and b we have the y values from the f curve greater than or equal to the y values from this g curve. Now, we broke up the region between a and b into n subintervals. For example, something like this, and we drew vertical lines at each of these subdivision points. And we called these subdivision points, for example, x sub 0, x sub 1. This last one could be x sub n. X sub 0 was synonymous with a, x sub n was synonymous with b. We might have had one in the middle somewhere, x sub I. And in each subinterval, and by the way, the distance between the successive x values we called delta x. This is just reviewing material that you had in your classes. We don't have rectangles yet, but in each subinterval, we could, for example, go over to the right endpoint. For example, the first subinterval goes from x0 to x1. At the right endpoint here at x1, go up until you hit the f curve. Whatever the height is here, use that to look the top of the rectangle, and go over to the same point, go down till you hit the g curve. Whatever the height is here, that's going to be the height, the level that you're going to use for the bottom of the rectangle. And doing the same thing in each subinterval. In the second subinterval, going to the right end point, going up till you hit the f curve, and using that height for the height of the rectangle, and going down until you hit the g curve, and using that to level off the bottom of the rectangle, and so on. So we could produce n of these rectangles in that manner. These are supposed to be, in this case, all delta x apart. On the ith subdivision here, we go up until we hit this point. This is the point xi comma f of xi, and this is the point x sub I over comma g of xi. It's on the f curve, so its y value is f of its x value. The area is then defined to be the limit of the sum of the areas of these rectangles as the number of rectangles grows very large. And the typical rectangle, the ith rectangle, has area base times height. The base, of course, is delta x. The height of the rectangle is the distance between these 2 points. Since they have the same x-coordinate, the distance is just a difference in their y-coordinates, f of xi minus g of xi. The limit of this Riemann sum symbolically is written as the definite integral from a to b. This became f of x minus g of x dx. In this manner, we developed a formula for finding the area between two curves. Now, there are some problems with this formula. First of all, when I hear f and g, these are basically throwaway names for functions. There is nothing that's expressing to me the idea that what I'm dealing with here is a high-low region. Okay, I would like something to indicate that f of x has to be greater than or equal to g of x, that the y value of this curve is greater than or equal to the y value of this curve, which means this curve is like the high curve and this curve is the low curve. So permit me to rename this function. Instead of f of x, let's call it y sub h of x, and let's call this one y sub l of x. In other words, meaning that in this region between a and b, the f curve is the high curve and the g curve is the low curve. So I'm going to change this to the integral from a to b of y h of x minus y l of x dx. The y value of the high curve minus the y value of the low curve from a to b. Now, what are a and b? Sometimes a and b are given explicitly. They are the vertical lines which bound this region. In other words, I'm interested in the region between these two curves and these two vertical lines. Sometimes the problem will be stated exactly like that. Find the area of the region bounded by two curves and you're given the two vertical lines. Other times, however, a and b will not be explicitly given. If a and b are explicitly given, fine, use them. If they're not explicitly given, then a is going to be the x-coordinate of the leftmost point in the region, and b is going to be the x-coordinate of the rightmost point in the region. So let me just write that down for you. If this is going to be our formula for area, a is going to be the x-coordinate of the leftmost point in the region, and b is going to be the x-coordinate of the rightmost point in the region. Now understand, this is going to be the y value of the high curve in terms of x, the y value of the low curve in terms of x. This is going to be a function of x. We're going to integrate with respect to x from x equals a to x equals b. A and b are going to be x-coordinates. Let's try some examples. Okay, for our first example, let's find the area of the region bounded by the two curves y equals 8 minus x squared and y equals x squared, and the two vertical lines x equals minus 1 and x equals plus 1. These curves, of course, are both parabolas. If you can't graph them on your own, you can use your graphing calculator. We'll be looking at that a little later on. But right now, y equals x squared, I assume most of you know how to sketch. It's the parabola vertex at the origin opening up like this. Y equals 8 minus x squared is also a parabola. It goes through, let's see, when x is 0, y is 8. And it looks something like that. We want to find the area bounded by these two curves and the two vertical lines, x equals -1 and x equals +1. X equals -1 looks like this. X equals +1 looks like this. And this is the region that we're talking about. Now, this is an exact example of what we just set up in general. We have certainly a high-low region. Now, in this case, every time I draw a vertical line in this region, it runs from one curve to the other and certainly gives me the feeling that this parabola is the high one and this is the low one. If that is the case, what is yh of x, yl of x, a and b, which I'm going to need in order to compute the area? The y value of the high curve, the y equals 8 minus x squared is the high curve. The y value of the high curve is 8 minus x squared. The y value of the low curve, that's the parabola y equals x squared. A and b are the x coordinates that were given. This is between x equals a and x equals b, so it's -1, +1. And the area here is going to be the integral from a to b of yh of x minus yl of x dx, or the integral from -1 to +1. yh of x is 8 minus x squared minus yl of x, x squared dx. The integral from -1 to +1 of 8 minus 2x squared dx. Now, there are two ways to finish off this problem. One is to use the fundamental theorem of calculus, which requires you to anti-differentiate this function and to evaluate it between the limits of integration. If we do that, we would get 8x, anti-differentiating the x, minus 2, x to the 3 over 3, between -1 and +1. We will evaluate this at the upper limit and subtract off what we get at the lower limit. Plugging in x equal to 1, we'd get 8 times 1 minus 2/3 of 1 cubed. Take away now at -1, 8 times -1 is -8. Minus 2/3 times -1 cubed becomes plus 2/3. This is 8 minus 2/3 minus a minus plus 8 minus 2/3, or 16 minus 4/3. Changing 16 into thirds, we get 48/3 minus 4/3 for an answer of 44/3 square units for the area. Now, we may also use our graphing calculators to perform at least an approximation to the value of this definite integral. Let me show you how you would do that. Okay, I have hooked my graphing calculator to an overhead projector, so what I punch into the calculator will be on the something that you can view on the board. Turn on my calculator. Let me just clear everything out. Okay. I would like to show you how to evaluate a definite integral using the graphing calculator. Whereas I would like to basically integrate 8 minus 2x squared between -1 and +1. This is my goal. I'm looking for the integral from -1 to +1 of 8 minus 2x squared dx. To get the approximation that the calculator gives you, I'm going to hit the math button and then option 9. So I hit math, that's the third button on the left. Then I can either scroll down or just punch in 9. And that gives me, when I hit math and then 9, it gives me function to be integrated, left parentheses. I am now going to put in 8 minus 2x squared. And a comma. The comma is right above the number 7. 8 minus 2x squared, comma. Then I want the variable x. Then you indicate the variable x. So I punch in an x and another comma. Then minus 1, comma, plus 1. Now the minus is not the subtraction sign, which is above the addition sign, but on the very bottom you'll see a minus in parentheses. That's for negative numbers. So minus 1, comma, 1, close parentheses. Function to be integrated, 8 minus 2x squared, with respect to x is the variable, from minus 1 to plus 1. And then I hit the enter button. And it gives me its approximate answer, 14 point, what looks to be like 6 repeating. Okay. Now let's say I want a fractional equivalent. There's nothing wrong with this answer. I can hit the button that says math. And the first option that says fraction, it's already lit up. So I hit enter. It says, I want to take this answer and turn it into its fractional equivalent. I hit enter again. There we get the 44/3. So even though it just gave us an approximation, when we hit it, it does give us the 44/3. It may not always come out this nicely. Sometimes you'll get something which is a little bit off, but here, because it is really doing an approximate integration, and you'll learn more about approximate integration in your calculus classes. But it's not a bad approximation. In this particular case, you do get a very nice answer. The answer is 44/3, or the 14.6 repeating, which is equivalent to the 44/3 square units. And this is achieved by hitting math 9, and you are prompted with a function to be integrated. Remember, you enter the function, comma, the variable x, comma, a, comma, b, close the parentheses, and hit enter. Okay, for problem number 2, I'm going to modify problem number 1. I want you to find the area of the region bounded by the 2 curves, and I'm going to stop it right there. That's my problem. Find the area of the region bounded by the 2 curves y equals 8 minus x squared and y equals x squared. Now, like before, I still have, the picture hasn't changed. Except now I'm not saying between x equals minus 1 and x equals plus 1, so I want the entire region bounded by these curves. So no one is giving you x equals a and x equals b. You have to find them. Now in this case, as I said before, a and b represent the x coordinates of the leftmost point and left and rightmost points in the region. Turns out in this case, and in most of the examples that you're going to be dealing with, unless you're explicitly given what a and b are, they're very often points of intersections of curves in the problem. So I need to find these points of intersections. There are 2 ways to do that. One way would be to solve simultaneously. We have y equals x squared, y equals 8 minus x squared. We can set the 2 y values equal to each other, giving us that 8 is equal to 2x squared is 4, x is plus or minus 2. Whereas here we have the point 2, 4. I found the 4 by plugging into either of the two equations. You should get the same answer. Minus 2 also, 4. So these are the points of intersection. Now, you don't need the y values except to check that, yes, 2, 4 is on this curve, 2, 4 is on this curve. What you really need are the x coordinates of these points, because they are going to be A and B. So, now, let's say you really are crummy at solving simultaneously. Well, the graphing calculator can help you once again. Let's go back over here and look and see how we would go about finding those points of intersection. I can turn to y equals. Let me clear out. I hit the y equals option. I'm putting in y equals 8 minus x squared for the first curve. Enter. Y equals x squared for the second curve. And then I'm going to hit graph. Right now, if I hit window, I see that I am on a somewhat limited window. I'm on the decimal window. I'm going to hit zoom and switch to the standard window, option number 6. That gives me minus 10 to 10 on the x and the y axes, and I got the picture that I have over here. Now, I want those points of intersection right over here. This is what I'm looking for. One way is to solve simultaneously. The other way is to ask your calculator to solve simultaneously. The way to do that is to enter, to hit second, then the calc key, and then option number 5. So I hit the second button, that's that yellow button in the upper left, then the calc key, which is above trace. Then those are the options. I choose 5, which is for points of intersection. And right now, it's flashing over there. Now, it doesn't know which point of intersection you want. It needs to be pointed in the right direction. So I'm going to send the cursor, the arrow that points to the left, over to that first point of intersection that I was looking for. And it says, right now, on the first, hit enter, the first curve, it says, tells you that that's where you are at minus 1.9, 4.3. And the first curve is the y equals 8 minus x squared. If you hit enter, it says second curve, it tells you that you're at the point minus 1.9, 3.66 something. Hit enter again. It's asking you for a guess of what your point of intersection is. As long as the flashing dot is somewhere near the point of intersection, it should work. Just hit enter again, and it'll give you the point of intersection, minus 2, 4. That was the first point of intersection that we found. If we want to find the other point of intersection, I mean, here we have a symmetric situation, but many times we don't. We have to repeat the procedure. We go, okay, let us second calc 5 again. However, now it's flashing in the wrong area, so I'm going to move my cursor that goes to the right over to where the other point of intersection is located. I'm going to hit enter once, twice, the third time it gives me the point of intersection of 2, 4. All right, so I know the points of intersection one way or another, and I'm now ready to proceed with this problem. Let's go back over here. I need to know what YH of x, YL of x, A and B are. The high curve, once again, is, of course, the 8 minus x squared curve. The low curve is y equals x squared. A and B are now minus 2 and plus 2, respectively, the x coordinates of the leftmost and rightmost points in the region. So the area is going to be the integral from minus 2 to plus 2 of the y value of the high curve minus the y value of the low curve dx. Once again, the integral from minus 2 to 2 of 8 minus 2x squared dx. Now, we could do this the same way we did it before, anti-differentiating and plugging in, or we can approximate it by hitting the Math 9 key and asking it to integrate the function 8 minus 2x squared with respect to x between minus 2 rather, and plus 2. We don't need the plus sign. Let's go over and do that on the calculator. If I want to get out of this situation, I'm going to hit second and quit. And I'm going to once again hit Math and 9. Function to be integrated. And I'm interested in 8 minus 2x squared, comma x, comma negative 2, comma positive 2. Hit enter, and I have 21.3 repeating. Square units for the area. If I want the fractional equivalent, I would hit Math. It's already on the fraction option. I hit enter, enter again. 64/3 square units. And that is, in fact, the answer that you get when you actually use the fundamental theorem of calculus, anti-differentiate, and plug in. For our third example, let's try the following. Find the area of the region bounded by the curves y equals x squared minus 4x plus 3 and y equals x minus 1. Once again, we have a parabola and a line. Let's go over to the graphing calculator. Let it draw the picture for us right now. I'm going to clear off what I have. Okay. X squared minus 4x plus 3. For the first one, enter, and x minus 1 for the second. Graphing it, and we have this parabola and this line. We want the points of intersection. Now these actually we can do freehand. Let me just copy the picture down for us over here. We have a parabola and the line, like so. The region that we're looking at looks like that, and it is a, once again, a high-low region. Clearly, in this region, the high curve is the straight line x minus 1, and the low curve is the parabola x squared minus 4x plus 3. Now that changes outside of the region with the parabola going higher than the line, but between here and here, that is the case. Once again, x equals a and x equals b will be the, a and b will be the x coordinates of these points of intersection. It is not hard to solve simultaneously here. Solving simultaneously, setting x squared minus 4x plus 3 equal to x minus 1, bringing everything over to one side. X squared minus 5x plus 4 is 0. Factoring this quadratic equation, we have x minus 4, x minus 1, checking x squared minus 5x plus 4, giving us x minus 4 is 0 or x minus 1 is 0. x equals 1, and x equals 4 as the x coordinates of these points. If x is 1, y in either of these is 0. If x is 4, y in either of these is 3. A and B are therefore going to be 1 and 4 respectively. And we're interested in the area, which is the integral from A to B, from 1 to 4, of YH, which is x minus 1 minus YL, which is x squared minus 4x plus 3 dx. Now, you can do this by simplifying, anti-differentiating, plugging in, or you can actually have the integration done on the calculator. If you want to enter it in other words, math 9, and you get the function to be integrated, if you want to enter it in the way it is, you're going to have to write left parentheses x minus 1 minus, right parentheses minus left parentheses x squared minus 4x plus 3, comma, x, comma 1, comma 4. Or you can simplify first and substitute in the simplified version here. Let's go over to the calculator and see what happens. First of all, if we wanted to get those points of intersection, let me just erase those dots from the previous problem. We're now looking for these 2 points of intersection. I would hit second, calc, 5, send the cursor somewhere over close to the first point of intersection, hit enter once, twice, 3 times, and there you have the point 1, comma 0. Hit second, calc, 5, send the cursor somewhere over to the second point of intersection, hit enter once, twice, 3 times. You have the other point of intersection, 4, comma 3. Then I hit second and quit to get out of that and to get into the main menu here. I hit math and 9. Now if I'm going to do it the way that I have indicated on the board, function to be integrated, I'm going to use left parentheses, x minus 1, right parentheses, minus left parentheses, x squared minus 4x plus 3, close parentheses, comma, x, comma, 1, comma, 4. If you make a mistake, the calculator will indicate that there's an error and it'll help you go to it. I hit enter and I get an answer of 4.5. Okay, and that is in fact the same answer that you would get if you did it by anti-differentiating and plugging in. 4.5 square units for the area of this region. Now here you had an option. You could either use the calculator or not. There are certain problems where without the calculator it would be very, very difficult. Let's try another example. Let's go to example number 4. Very similar problem, but now I want to find the area of the region bounded by the curves. And this time, the curves are y equals x to the 4th minus 2x, and y equals 3x minus 1. And I'm going to basically do this entire problem on the calculator. So let's go over and have the calculator do the sketch for us. Let's clear off what we have here. Y equals, I'm going to clear the 2 functions that were in from the previous problem. X to the 4th minus 2x, and then the power symbol, which is above the division symbol, x to the 4th minus 2x, enter, then 3x minus 1. Then hit graph. Picture is very similar to what we had before, except it's a 4th degree curve. It's a little skewed over there. It's not exact, it's not a parabola. But we have something like this. And the line goes somewhere like this. And we're looking for these 2 points of intersection. If you try to just do this by solving simultaneously, you will not get nice points of intersection with integer coordinates. This one you really have to do using the calculator. We don't have to, but it's certainly going to be easy on the calculator. A problem like this might be indicated, carefully sketch the region bounded by these curves, labeling all points of intersection accurate to the nearest tenth, and then find the area. Use your calculator to find the area of the region bounded by these 2 curves. Okay, so I need those points of intersection. Let's see. I'm going to hit second, calc, 5. The cursor is in that vicinity right now. So I'm going to hit enter, enter, enter 3 times to get the point which is to the nearest tenth, 0.2 comma minus 0.4. That is this point, 0.2 comma minus 0.4. Now I need this other point of intersection. So I hit second, calc, 5. But I have to send the cursor over to that second point of intersection. And when it's flashing in that vicinity, it doesn't have to be right on it, but close enough, hit enter, enter, enter. Tells me the other point of intersection is about 1.6 comma 3.9. So the area is going to be the integral from A to B, from the x-coordinate of the leftmost point to the x-coordinate of the rightmost point, from 0.2 to 1.6, y value of the high curve. The high curve here is a straight line, once again, 3x minus 1. The low curve is x to the 4th minus 2x. And I'm going to get this on the calculator by hitting math and 9. Let's first quit where we are, second, and quit. Math and 9, function to be integrated. Okay, left parentheses, 3x minus 1, right parentheses, minus left parentheses, x to the 4th minus 2x, close parentheses, comma, x, comma, 0.2, comma, 1.6, close parentheses, hit enter, and we get about 2.803, or about approximately 2.8 square units. We are only taking the points of intersection to the nearest tenth, so let's not pretend that this has any big degree of accuracy. So about 2.8 square units. Another option that you might be interested in is the following. When I hit math 9 and I get function to be integrated, instead of actually writing this in, I've already entered these functions, these values in for the curves that I had. If we go back to the y equals menu, this was y2, this was y1. This was known as y sub 2. This was known as y sub 1. Another option that's open to you is to actually, you've already put this in, to say I want to integrate y2 minus y1, comma x, comma 0.2, comma 1.6, and this should give you the same answer. Let's see how we do that. Let's go. Let's quit this. Instead of what we have there, I'm going to hit now Math and 9. Now, go over to where it says Variables. The VAR, it's the third row right next to the clear button, Variables. And go to put the cursor over to Y Variables. It says Function, hit Enter. And I want Y2 first. So go down to 2, or just hit 2. If I go down to 2 and hit Enter, it gives me Y2 minus, repeat that, Variables, over to Y Variables, go to Function, and now already have Y1, so that's what I want, comma, X, comma, 0.2, comma, 1.6, close it up, hit Enter, and you get the same answer. Now, the first time you're doing this, it seems awkward, but after a while, it's certainly a convenient way not to have to rewrite the functions. You've already put them in just to learn how to do Y2 minus Y1. That's over at Variables. You take the option to Y Variables, and then you just get whatever you need.